right, back in the shop after a couple-week absence. Took a boat trip, had a blast with some friends. So we're back at home and I've got another project. What would you expect, right? So I'm going to work on my bulldozer. I've got a project to use the bulldozer for, which is to fix a drainage issue in my driveway. But I need to modify the dozer to improve its reliability in the drivetrain. So I'm going to upgrade the drive line, similar to the upgrade for the motor grader that I did several months ago, I don't know, 3 or 4 months ago. And the second is to change the way the blade works and operates. And I'll show you the current drive line, and then I'll show you how the blade's working, and we'll talk about what I have in mind for the upgrades. So nothing too extensive, but I think they'll improve the reliability of the drive line, though I haven't had any issues with it. On the motor grader, I had damaged or wore, I don't know if it's damaged, but several of the drive belts failed. From what I think is premature. Now, I had a lot more operating time on the motor grader than I've had on the bulldozer. So I don't know for a fact that even though the drive lines as installed on these two pieces of equipment were nearly identical from the beginning, I haven't had the belt failures on the dozer. It could be that limited operating hours on this machine compared to the motor grader, which I've used more frequently, or there's something else about the motor grader that caused failures that isn't on the dozer that I may not fully understand. Anyway, I'm so much happier with the centrifugal clutch arrangement that I put on the motor grader that I'm going to make the same change to the dozer. And at the time I built these pieces of equipment, I was unable to find centrifugal clutches that would work the way I needed them. In other words, twin belt, at least 15, capable of 15 horsepower, power transmission. So I have found that type of clutch. So I've ordered another one for this machine, and we'll get into its installation. But let me show you the current drive line for those of you that missed the motor grader episodes 3 months ago where we upgraded that drive line. I'll show you what I've got here, and I'll also show you the issues I'm having with the blade. So we'll get into that. What you doing, Butchie boy, huh? What you doing, huh? It's raining pretty hard outside. It's raining pretty hard outside, yeah. Look at you. Look at you. Give me that paw. Yeah. Big paw. Look at the size of that paw. That's a big dog. Okay. All right, so we'll go over here to the dozer, mini dozer. And I have two issues, as I mentioned, the drive line and the blade operation. So let me show you the issue I have with the blade operation first. Okay, so there's no float function in the hydraulics, and that may be what I need to do, is establish a float function. I wanted to be able to operate the dozer with the blade, just the weight of the blade, and let the blade kind of follow the terrain contour with just the weight of the blade downforce. So that would allow the blade, to just push gravel without having any mechanical pressure on the blade, and let it follow the terrain. As you know, a dozer with a short wheelbase, anytime you hit a bump, if the bump here lifts the front of the track up an inch, the blade's going to go up 1.5 inches or 2 inches. So maintaining, a level grade is difficult, especially on this tractor, because the hydraulics are not as quick acting as you might want them to be, since they are the hydrostatic transmission hydraulics, and we've discussed that with the motor grader. It's 600 psi with a couple of GPM, so you don't have instantaneous reaction of the blade to the controls. A weakness of this machine's design to some extent, but I solved that by allowing the blade to float mechanically. I don't have it built into the hydraulic circuit, but I wanted the blade, just the weight of the blade, to be able to push it along to level out the driveway, for example. So the way I did that is I disconnected the lift mechanism for the blade and let it float. So this is a bracket here. And get this off. Okay, so you see that there's a slot here, and the pin, which is connected to the lift cylinder here, can float in this slot. So that allows the blade's arms to float, and hence the blade will float. But what it does is it also shortens the distance that the cylinder can raise the blade off the ground. So there's two factors here. One, if I brought this pin down to this hole, which is a non-float location, that'll give me a little more lift. If I brought it all the way down to the arm and bolted it to the arm, I'd get even more lift. If I brought this connection point back on the arm, closer to the pivot, bring it back here, for example, I would get even more lift out here at the end of the arm. So there are several things I can do to increase the lift of the blade, which I need to do, is either move this connection point back, which would still give me float, but also give me more lift because it'll be further back and closer to the pivot point. So that would be one solution. The only concern here is potential interference with the tracks, clearance here. I think I have enough clearance to do that. The other possible interferences with the cylinder on the cylinder mount. So there are some other considerations I would have to deal with. So I like to keep the float. This is a mechanical float. I like to keep a mechanical float. Solved me from trying to convert to a hydraulic float, and which I may ultimately wind up doing. So I need to do some research on that. So the first thing, I think the easiest thing to do here is go ahead and pull this arm off. Unbolt this. See about moving this back on the arm. Make sure I have clearance to do that, and then drill another hole in this arm and move this connection back. So I think that will give me a little more lift and still be able to maintain this mechanical float function. See if I can avoid spilling too much fuel here. Watch me be unable to find those nuts when I need them to put it back together. I'll forgot that I put them on these studs. What we're going to do, I'm going to go ahead and take this front grill off. It's just 2 bolts here, so it's easy enough to do and get it out of the way. They make it a little bit easier to access the So this will give you a little better view for those of you that didn't see the motor grader video or don't remember. So in this position, this handle up, this tensioner pulley right here takes the tension off the belt, so the belts are loose, so the engine can crank without turning the transmission, and then and that point is spring loaded and puts tension on the belts, and so now the tensioner pulley keeps the belts on the engine pulley and the drive shaft pulley, which is down below. The rusty cylinder down there is the drive shaft. So, okay. That gives you an idea of what's going on here. It's pretty functional. I mean, it's completely functional. In this case, you know, it works fine. So, but it does require me to reach around the engine and flip this lever down, that sort of thing. So by putting a centrifugal clutch on the engine crankshaft, eliminates that, and we can just start the engine up without engaging the transmissions at all and increase engine speed, and the centrifugal clutch will engage, drive the transmissions. All right, let's get the muffler off. One of the things so attractive about these Cub Cadets is they're so easy to work on because everything is either 1/2 inch or 9/16. So 95% of the fasteners. Normally this is bolted here, but I didn't have clearance because of this lever, so I had to pull the muffler over. So normally it's bolted right here as opposed to I had wound up tack welding it there. Another compromise made because, you know, I needed the space for this operating lever. All right, this gives us pretty good access. Let's see. Get these belts off. So these belts are actually in very nice shape. Despite the way they're have been tensioned. Okay. All right, these are the two drive controls. This arm controls the front transmission, which drives the right track. This one controls the left transmission, or the rear transmission, which drives the left track. This is just friction material. So, okay, the drive shaft runs here from through a pillow block bearing all the way back to the rear transmission back here. So, all right, we need to split the drive shaft to get the old belts off. Or actually, yeah, I need to do that because I need to get the new belts on. I was going to say, I could just cut the belts off, but then I wouldn't be able to get the pulley out. All right, I need to, been a while since I've looked at this. I don't know, through several years. Okay, so let's see how this will work here, if I can do this. All right, so you can see the pillow block bearing there. It's got two bolts that go into a cross member. This drive shaft, you know, continues to here. Now, I'm going to show you on the other side of the pillow block bearing. There's a flex joint. Come out of here, go in here. Okay, so this is a flex joint. This is the remainder of the drive shaft. So I just undid this flex coupling. So normally this section of drive shaft has a yoke on it. It bolts to this rubber disc, and the rubber disc then bolts to another yoke on the other side. So this goes through the pillow block bearing. There's a similar flex coupling right here. See if we can get a picture of it. So that goes into the other transmission. So that's how the drive line is set up. Flex couplings, which are typical on the Cub Cadet drive line. And you can see this pin is most of the way out. Got the pin out. Let's see if we can move this shaft. All right, well, I just was able to move this. All right, so this is my drawing, life-size drawing of the bracket that the tensioner will bolt to. Has a curved slot here and a pivot point here. So the tensioner pulley is mounted to a bracket which will mount here and pivot on here to tighten it. I'm just going to cut this out roughly to see how it fits. Before I design it in CAD, and actually this is CAD, cardboard aided design. There's a jog in the frame. For those of you that are new to the channel, this is my Langmuir Systems Crossfire Pro plasma table. I've had it for about 5 years, and this has a cutting envelope of 3 feet, roughly 3 feet by 4 feet, capacity of 1/2 inch to potentially 5/8 of an inch plate steel. And what I got now on the table is some 3/8 inch, and I got a piece of 1/4 inch, but I'm going to cut some 3/8 inch mild steel, or A36 structural steel is also what it's called. And this is going to be the bracket for the tensioner pulley. We looked at made a cardboard cutout of it. I tested it, looks like it'll fit. This is the bracket. So the way it'll work is this will be bolted to the top like that, and this will pivot, and this bolt will go through a slot, and that's how we'll tension the belts. All right, so I turned the pump off because it's filled the table, or largely filled the table, and my air system is charged. All right, so this is the plate I cut out on the plasma table. Somehow lost the footage of it, but it's the design I modeled, and of course this is how the pulley will move in that slot. Tighten that bolt, tighten the 2 bolts to tension it. So put a couple of belts on here just temporarily. Approximate position. All right, so this bracket will get welded to the frame, and the pulley will be able to rotate that way to tension the belt. All right, so I think that'll work fine. I can't do much more at this point until I get the centrifugal clutch, which is a different diameter. So I'm going to have to wait until I get that in order to do some more on here. We'll take this pulley off. There's a tapered sleeve here, a couple set screws. We'll pull it out. Sleeve will come out. The hub will come out. The tapered hub. We'll be able to remove the pulley easily. When I get the clutch, then we can put that on and determine, the belt size that we need, and then we can install the tensioner. So I have to wait for that. All right, folks, that's it for this episode. I'm going to have to stop now until I get the centrifugal clutch. As I said, we'll be able to determine the proper belt size, and I can install the tensioner pulley. I think that's going to work fine. Now, this is different from the way I did the motor grader. If you guys watched the motor grader video, I actually hinged the engine and used some jack screws to tighten the belts. I don't have enough room in the frame to do that on this machine. So I think this tensioner pulley, pretty conventional way of tensioning belts, will work fine. As I mentioned before, when I originally did this, I could not find a double belt pulley with a clutch. So I don't know whether I looked in the wrong place or someone just started making them. I don't know. Anyway, the idea of having the 2 belts there is redundancy. So if a belt breaks, I still have 1 belt driving the transmissions. I can limp home, right? In reality, 1 belt's enough to drive the tractor, to carry the 15 horsepower or 14 horsepower, because it's a high-speed, low-torque application. It's 3,600 RPM. So the belt will be fine in that situation because it's geared down so much to a couple RPM on the sprockets in the driving the tracks. So, but the second belt does give me the redundancy. So if I break a belt, I don't have to immediately replace it. I will leave a couple extra belts around the drive shaft so that I'll be able to easily pull another belt up, slide it on the pulleys, retension it. It'll be, be easy. You don't have to split the drive shaft like I had to do here. So we'll come back next time working on that, and I've got an interesting idea for the way to get the blade to float. I mentioned I wanted to get it to float, so I got an idea. I think it's going to work. We'll see. So next time we'll pick it up there. Thank you for watching. Subscribe if you haven't already. Ring the notification bell. Give a thumbs up if you enjoyed the content. We'll see you next week.